think for a moment about something seemingly obvious. Why a feather drifts gently to the ground while a stone drops like a stone.
Hmm.
Or how a colossal aircraft carrier, a city on water, stays afloat while a tiny coin just vanishes into the depths.
Right.
This simple act of floating and sinking actually unlocks some incredibly profound and surprising scientific principles.
Exactly. Today, we're plunging into the fascinating realm of fluid mechanics. We're going to explore the core concepts of upthrust, buoyancy, Archimedes' principle, and, the fundamental science behind why things float.
Okay.
Our exploration will be based on some really solid educational materials that clearly lay out these essential physics ideas.
And our goal with this deep dive is to go beyond just defining these terms, right?
Yeah,
We
absolutely.
want to unpack them in a way that sparks genuine understanding and maybe reveal some of the more unexpected implications and practical applications.
Aiming for those aha moments.
Yeah. Exactly, without leaving you feeling like you're drowning in information. Okay, let's get started. Let's untangle the ideas of upthrust and buoyancy first.
Okay, so upthrust, which you might also hear called buoyant force,
Mm-hmm.
often written as a fluid hazard. It's the upward force that a fluid exerts on any object placed within it.
And by fluid, you mean liquids and gases.
Yes, both liquids and gases.
Yeah.
Whether the object's fully submerged or just, partially dipped in. Buoyancy, then, is simply the property,
Yeah.
the capacity of that fluid to exert this upward push.
Okay. The sources we've looked at have a couple of really clear examples of this. Like, imagine trying to push an empty sealed can down into a tub of water.
Right.
You feel it pushing back against you, don't you? More and more the further you push it down.
Mm-hmm. And then let go.
And the second you let go, pop, it shoots right back up.
Yeah. It's a similar story with a cork. Try to force it underwater and it resists.
And it just bobs back to the surface with only a part of it staying submerged when you release it.
What's really interesting here is the battle of forces going on. So every object has weight, W, pulling it downwards because of gravity.
Sure.
At the same time, the fluid is exerting this upward upthrust, $50. Whether something floats or sinks depends entirely on how these two forces balance out.
So floating happens when they're equal?
Exactly. Floating happens when the upward push of the upthrust exactly equals the downward pull of the weight. W equals 5 FU.
And here's where it gets really intriguing, I think. This upthrust, it isn't a fixed value, is it?
No, that's a crucial point.
Yeah.
As you submerge more of an object in the fluid, the upthrust actually increases.
Okay.
It hits its maximum strength, let's call that FBL, when the object is completely underwater.
Right.
This maximum upthrust is the critical factor. It determines if an object will slate entirely, partially, or just sink straight to the bottom.
Okay, so that maximum value, $50, that's the key number.
That's the key. Our materials clearly state the conditions. If this maximum upthrust, FBL, is equal to or greater than the object's weight, W, then the object will float. If FURB is greater than W, you'll see it floating with only a portion below the surface. If FBR is exactly equal to W, it'll float fully submerged, sort of hanging there in the fluid.
Okay. And in both those floating cases, it feels weightless in the water.
Pretty much. Its apparent weight is zero.
Now, what happens if that maximum upward push just isn't strong enough? If $50 is less than W?
Well, then it sinks. If FE$ is less than W, the object will inevitably sink. There's a leftover downward force, W minus FBR, which causes it to accelerate downwards through the fluid.
Got it.
And it's also worth remembering, as our sources remind us, that gases are buoyant too. Think about a helium balloon.
Oh, yeah, rising up.
That happens because the upthrust from the surrounding air is actually greater than the total weight of the balloon and the helium inside.
Huh. We don't usually feel that air buoyancy on ourselves, though, do we?
No, not really, because it's incredibly small compared to our own weight. But it is there.
Okay, so upthrust and buoyancy are all about this upward push from a fluid. What are the sort of main characteristics or rules that govern this force?
Our materials highlight three important properties. First, the upthrust is directly related to how much of the object is submerged, the volume.
More volume underwater means more upthrust.
Exactly. The more volume you displace, the greater the upward force.
Mm-hmm.
Remember pushing the can or cork deeper?
Yeah, you feel more resistance.
That's it. A classic example is why a feather and a pebble of the same mass fall differently in air.
Right, the feather drifts.
The feather, with its much larger volume for its mass, experiences a significantly greater upthrust from the air, and air resistance, of course, than the compact pebble, so it drifts down.
But in a vacuum?
In a vacuum, no air, no upthrust, they'd fall at exactly the same rate.
Okay, that makes intuitive sense. More bulk in the water, more pushback. What's the second key property?
The second property is that if you keep the submerged volume the same, the upthrust will be stronger in a denser fluid.
So the type of fluid matters too.
Definitely. Our sources use the example of placing identical corks in, say, water, and then in glycerin, or even mercury, which is super dense.
Okay.
You'd see the cork in the denser fluid. It floats higher. Less of its volume is submerged.
Meaning the denser fluid is pushing up more strongly.
Precisely. In fact, you'd have to push down harder to get it to the same depth as the cork in water,
Yeah.
indicating a stronger upward force from the denser liquid.
So it's not just about how much is under, but also what it's under. Got it. And the third characteristic.
The third property concerns where this upthrust force actually acts on the object. It acts upwards through a specific point called the center of buoyancy, often labeled B.
Center of buoyancy. Okay. What determines where that is?
It's essentially the center of gravity of the fluid that the object has displaced. The object made in the fluid, you could say.
Okay. The center of gravity of the missing fluid.
Exactly. Now, if you have a uniform object that's fully submerged, this center of buoyancy is in the same place as the object's own center of gravity.
Maybe.
But if the object is floating, like partially submerged, then the center of buoyancy, B, will be located below the center of gravity, G, of the entire object.
Right, because B is the center of just the underwater part's displaced fluid, while G is for the whole object. Okay. Now, let's dig into the why. What's the fundamental reason this upward force exists?
The underlying cause is the pressure difference within a fluid. We know that pressure increases the deeper you go, right?
Yeah, more stuff on top of you.
Exactly. So picture a simple block submerged in a liquid. The pressure pushing upwards on the bottom surface of the block is greater than the pressure pushing downwards on its top surface.
Because the bottom is deeper.
Precisely. This difference in pressure, acting over the areas of the top and bottom faces, results in a net upward force, and that's our upthrust.
And the sideways pressures.
They cancel out. The pressure at a certain depth acting on one side is balanced by the equal pressure on the opposite side.
Okay, so it's the pressure difference with depth. That makes sense. Our sources also mention something about a very thin sheet, a lamina.
Yes, good point. They point out that if you immerse a very thin sheet, or lamina, horizontally in liquid, well, the difference in depth between its top and bottom surfaces is tiny.
Almost zero.
Right, so the pressure difference is practically negligible. Consequently, the upthrust on it is minimal, and it'll just sink due to its own weight.
Got it. Okay, we've got a good handle on upthrust, buoyancy, and the reasons behind them. Now it's time to bring in the big gun, Archimedes.
Ah, yes, Archimedes.
What exactly does Archimedes' principle tell us?
Archimedes' principle is really a cornerstone here. It elegantly states that the upthrust experienced by an object submerged in a fluid is exactly equal to the weight of the fluid that the object displaces.
Equal to the weight of the displaced fluid. Okay.
Our sources even walk through a mathematical proof. Imagine cylinder underwater. You calculate the upward force on the bottom face based on its depth and pressure, and the downward force on the top face.
Right.
The difference between those two forces is the net upward force, the upthrust, phi b Zeller. And when you work it out, it comes out as VIHO G GO.
Where V is the submerged volume, granular is the fluid density, and G is gravity.
Exactly. And crucially, VEG is also the formula for the weight of a volume V of fluid with density, the AE. It's the weight of the displaced fluid.
So the volume of the object underwater and the density of the fluid, that directly gives you the upthrust force.
Precisely. And what's remarkable, as our materials emphasizes, is that this isn't just for simple cylinders. It applies to objects of any shape, however weird or irregular.
Okay.
And one of the most noticeable effects of this upthrust, which Archimedes famously twigged to, is the apparent loss of weight an object seems to have when it's in a liquid.
We've all felt that, haven't we? Lifting a heavy rock underwater feels so much lighter.
Exactly. That's the buoyant force helping you out, counteracting gravity.
Yeah.
Our sources also mention things like, a fish feels lighter in water, and even super-sensitive scales can detect a tiny weight difference for an object measured in air versus in a vacuum because of the air's buoyancy.
So, to state it formally then, Archimedes' principle is, when a body is partially or completely immersed in a fluid, it experiences an upthrust equal to the weight of the fluid it displaces.
That's it.
And this applies to both liquids and gases.
Absolutely correct. The principle holds for all fluids.
This is such a fundamental idea. How can we actually, see this in action? Our sources describe a couple of experiments.
Yes, they do. Two neat ones. The first uses two cylinders with the exact same volume. One solid, the other's hollow.
Okay.
You hang them from a balance. Then you dip the solid cylinder into water. The balance tips, right? Because the solid one seems lighter now.
Due to the upthrust.
Exactly. Now you carefully pour water into the hollow cylinder until the balance levels out again.
I see.
Since the cylinders have the same volume, the weight of water you just poured into the hollow one must be equal to the weight of the water the solid one displaced. And that amount perfectly balanced the buoyant force.
That's clever.
Right.
Directly comparing the buoyant force to the weight of the displaced water. What's the second experiment?
The second one uses a spring scale and a eureka can.
A eureka can. Right, the
Yep.
one with the little spout.
That's the one, designed to collect overflow precisely.
Yeah.
So first, you weigh a solid object in air with the spring scale. Note the weight.
Okay.
Then, you fill the eureka can right up to the spout. Carefully lower the solid object into the water. It displaces water, which overflows through the spout into, say, a measuring cylinder.
Right.
You note the new, lower reading on the spring scale. That's the apparent weight in water. And you measure the volume of water you collected.
And they should match up.
Exactly.
Yeah.
The experiment shows that the loss in weight, weight in air minus weight in water, is exactly equal to the weight of the water collected. Our materials even give numbers, like 300-gram force in air, 200 in water.
So a loss of 100 gram.
Right. And you'd find you collected 100 milliliters of water, which weighs 100-gram force. It confirms the principle perfectly.
Tangible proof. Okay, so that links the buoyant force to the displaced fluid's weight. Now, let's circle back to the big question. Why do some things float and others sink? How does density really lock this down?
Density is absolutely central. Our sources explain that an object's fate in a fluid depends entirely on how its density, let's call it leucarials, compares to the fluid's density.
Okay, the comparison is key.
Three cases. One, if the object is denser than the fluid, it sinks. Its weight is just greater than the maximum possible upthrust the fluid can provide.
Makes sense. Too heavy for the push.
Two, if the object's density is exactly the same as the fluid's density, it floats fully submerged. Weight perfectly matches the maximum upthrust, it just hangs there.
Right, neutral buoyancy.
And three, if the object is less dense than the fluid, it floats partially submerged.
Like the cork.
Exactly. In this case, its weight is less than the maximum possible upthrust. So only enough of it goes underwater to displace a weight of fluid equal to its own total weight. Then the forces balance, and it floats happily on the surface.
The classic iron nail sinking while a cork floats is the perfect example, isn't it? Even if they weigh the same.
It is. The nail is far denser than water. The cork is much less dense.
So density is the decider.
Pretty much. And as the sources likely mention, if you just tossed a bunch of different materials into water, you'd see this play out. Wood, ice, oil less dense, they float. Rocks, metals denser, they sink.
But what about giant steel ships? Steel sinks.
But it's the average density that matters for the ship. Although the steel is dense, the ship's hull encloses a massive volume of air.
Right, mostly empty space inside.
So you take the total mass, steel, engines, cargo, and all that trapped air, and divide by the ship's total volume. That average density is much less than water's density, so it floats.
That average density concept is crucial. Okay, let's shift slightly to relative density. What is that and how does it fit in?
Okay, so density itself, as the sources define it, is just mass per unit volume. Kilograms per cubic meter or grams per cubic centimeter. Simple enough. Relative density, often called RD or sometimes specific gravity, is a way to compare a substance's density to a standard. And that standard is almost always pure water at 4 degrees Celsius.
Why 4 degrees Celsius specifically?
Because that's the temperature where water is at its maximum density. So it provides a consistent reference point.
Okay, so relative density is a comparison, a ratio.
Exactly. It's defined as the ratio of the density of a substance to the density of water at 4 degrees C. Or you could think of it as the ratio of the mass of a certain volume of the substance to the mass of the exact same volume of water at 4 degrees C.
And because it's a ratio, no units.
Correct. Relative density is a pure number, dimensionless.
So how does this RD value relate back to the actual density, like in kilogmO?
Our materials point out a very convenient link. In the CGS system, where water's density at 4 degrees C is 1 GCMO, the numerical value of a substance's density in GCML is exactly the same as its relative density. Oh, Andy, very. In the SI system, where water's density is 1,000 kilogemalida, the density of a substance in kilometer is just its relative density multiplied by 1,000.
So RB is like a shortcut related to water's density?
Pretty much. It tells you immediately how many times denser than water a substance is.
Okay. Now, how can we use Archimedes' principle to actually measure this relative density? Say, for a solid,
Archimedes gives us a really neat way. For a solid object that's denser than water and doesn't dissolve in it, you weigh it in air, then you weigh it while it's fully submerged in water.
okay, get those two weights.
Then the relative density is simply the weight of the solid in air divided by its apparent loss of weight in water.
Weight in air divided by weight in air, weight in water.
Exactly. And remember, that loss of weight is the buoyant force, which Archimedes tells us equals the weight of the displaced water. So the formula is really weight of body, weight of equal volume of water.
Clever. What if the solid dissolves in water?
Good question. You'd have to use a different liquid, one it doesn't dissolve in, and one whose relative density you already know. You do the same weighings in air and in that liquid. Then there's a slightly modified formula involving the RD of the liquid used.
Okay. And what about finding the relative density of a liquid itself?
For a liquid, you need a sinker, a solid object that sinks in both the test liquid and in water, and doesn't dissolve in either.
Right.
You weigh the sinker in 3 situations: in air, submerged in the test liquid, and submerged in water.
Okay. Air, liquid, water.
Then the relative density of the liquid is the ratio of the weight loss of the sinker in the liquid to the weight loss of the sinker in water.
So weight in air, weight in liquid divided by weight in air, weight in water.
That's the one. Again, it works because the weight losses are equal to the weights of the displaced fluids, the test liquid, and the water by the same volume, the volume of the sinker.
So careful weighings let us figure out densities indirectly. Right. Let's tie this back together now with the principle of flotation itself. We've talked density, we've talked Archimedes. What's the core principle for floating things?
Okay, the principle of flotation builds directly on Archimedes. When an object is floating, whether it's bobbing on the surface or fully submerged but stationary, it's in equilibrium.
Meaning forces are balanced.
Exactly. The downward force is its weight, WU, acting through its center of gravity, G. The upward force is the upthrust, F. Tesla-Meller, acting through the center of buoyancy.
And for it to float, those must be equal.
Precisely. The principle of flotation states, the weight of a floating body is equal to the weight of the fluid displaced by its submerged part. So $1 equals FB.
That's the condition for floating?
Yes. And a direct consequence is that the apparent weight of any floating object is 0. It's fully supported by the fluid. If you put a floating boat on a giant scale underwater, it would read 0.
Makes sense. If it's just sitting there, not sinking, no net downward force.
Exactly. And from this principle, date FBVIO, we can derive a really useful formula relating volumes and densities.
Yeah.
If E is the volume of the submerged part of a floating object, and V is its total volume, and if the object's density and the liquid's density there is, then the ratio of VI equals the ratio of Wicks.
So the fraction of the object submerged is equal to the ratio of its density to the fluid's density.
That's it. Which explains why a cork, maybe with a density 1/4 that of water, floats with only 1/4 of its volume submerged.
And icebergs.
Icebergs, too. Ice density is about 90% of seawater density. So Leaser is about 0.9. That means a Sci-Vol is 0.9 cents. 90% of the iceberg's volume is hidden underwater.
Wow. That's a really clear link between density and how high something floats.
Yeah.
Okay, these principles are everywhere. What are some key real-world applications our sources highlight?
Oh, loads. Ships, obviously, are a huge one. We talked about the average density.
Right, the steel sinks, but the ship shape floats.
Exactly. And sources mention how a loaded ship sinks lower, more weight needs more displaced water to balance it. That's why they have the Clemson line.
The safety mark on the side.
Yes, to prevent overloading. Also interesting, unloaded ships use ballast-heavy stuff low down to lower their center of gravity and make them more stable.
And ships float higher in salt water than fresh water.
They do. Seawater is denser than river water, so it provides more upthrust for the same submerged volume. The ship needs to sink less to displace its own weight in the sea.
Okay. What about us, people floating?
Our average density is key. It depends on bone, muscle, fat, and crucially, air in our lungs. Take a deep breath, and your average density might drop below water's density, letting you float.
Easier in the sea, though.
Generally, yes. Denser salt water gives more buoyancy. And in the Dead Sea, which is incredibly salty and dense,
You just lie back and read a newspaper, practically.
pretty much, floating is almost effortless there.
Submarines must be masters of this.
Absolutely. They use ballast tanks, flood them with water to increase average density and dive, pump the water out with compressed air to decrease density and surface. It's precise buoyancy control.
And icebergs again? Floating islands of ice?
Yep, floating because ice is less dense than water. We mentioned the 90% submerged part. That's the danger to ships, the hidden bulk.
And if floating ice melts, the water level doesn't change.
Correct. It's a neat fact. The volume of water the melted ice adds is exactly equal to the volume of water the submerged part of the ice was already displacing. So no change.
Huh. What about nature? Fish?
Many fish have a swim bladder. It's like an internal balloon they can inflate or deflate.
To control their buoyancy.
Exactly. Adjusting the gas lets them rise, sink, or just hover at a certain depth without constantly swimming up or down. Very efficient.
And finally, balloons. Helium balloons, hot air balloons.
Same principle, but in air. Balloons filled with a gas lighter than air, like helium or just hot air, which is less dense than cool air, experience an upward buoyant force from the surrounding, cooler, denser air.
So the upthrust is greater than their weight.
Right, initially. So they rise. They keep rising until they reach an altitude where the outside air becomes thin enough, less dense, that the upthrust exactly balances the total weight. Then they stop rising.
It's really amazing how these fundamental ideas connect so many different things.
It really is.
So just to quickly recap, we looked at upthrust, that upward push from fluids. Archimedes' principle telling us that push equals the weight of the fluid displaced.
Yep. 5 up it all away is weight of displaced fluid.
And the principle of flotation for something to float, its total weight must equal that buoyant force, meaning its weight equals the weight of the fluid its submerged part displaces.
Exactly. Buy up EL away chases FDO dollars for floating objects.
And we've seen how these seemingly simple rules govern everything from huge ships to tiny fish floating in the Dead Sea, balloons in the sky.
It paints a picture of these invisible forces constantly at work around us.
It definitely gives you a new perspective. Okay, so here's a final thought to maybe chew on. While we've hit a lot of applications, think about other, maybe less obvious ways these buoyancy principles might be working. In nature, maybe, or in technology we use daily that we didn't specifically mention.
Yeah, keep it.
You might be surprised where you spot these fundamental forces doing their thing.